is Mrs. Essenbaum, and this is a video on covalent bonding and specifically the properties of covalent compounds or molecules, because covalent compounds means molecules. So just to remind you that covalent compounds are formed when nonmetals, so the elements in green, and other nonmetals get together and bond. And when they do this, they share electrons. So a covalent bond is the strongest of the three bonds that we've talked to. It's stronger than an ionic bond, and it's stronger than a metallic bond. What we're going to focus on today is discussing the properties of covalent compounds. So this is a table of the properties of covalent compounds. You have this table in your note packet that you're going to fill in the properties. And then we're going to spend some time right now talking about the explanation. So what we see is that covalent compounds tend to have low melting points and low boiling points compared to ionic compounds. We can find them as gases, liquids, and solids at room temperature, and they do not conduct an electric current when dissolved in water. So let's first talk about this first one. Why do they have low melting points and low boiling points compared to ionic compounds? So let's start by looking at an ionic compound, one that we're very familiar with, sodium chloride, or NaCl. Now, what is holding this sodium ion to this chloride ion is an ionic bond. And although ionic bonds are weaker than covalent bonds, they're still strong enough that it's hard to break them. Now, if I want to melt an ionic compound, so if I want to melt sodium chloride, NaCl, what I need to do is actually pull those ions apart. So I need to take this sodium ion and pull it away from that chloride ion, and take this chloride ion and pull it away, and I need to pull the ions apart. That involves breaking a ionic bond, and that requires a lot of energy. And so things like salt do not melt very easily. You have to melt them at pretty high temperatures. That's why when you put salt in a frying pan, it doesn't form a sticky mess. Sugar is different. Sugar is a covalent compound. So imagine that these purple molecules represent any covalent compound or molecule. It could be anyone. It could be H2O, it could be glucose, C6H12O6, it could be ammonia, NH3. Now, holding this purple dot together is the covalent bond. But this molecule here is being held to this molecule here by what we call intermolecular forces. So right here, what's holding these molecules together are between molecular forces. So intermolecular forces are forces between molecules. And it turns out that intermolecular forces, they're not a bond, and so they're weaker than ionic, they're weaker than metallic, and they're way weaker than covalent. So in covalent compounds, when I want to melt them, what I need to do is pull this molecule away, and all I have to do is break that intermolecular force. And it doesn't take a lot of energy to break that intermolecular force, because all I have to do is overcome weak intermolecular forces. The other property we're going to talk about is the fact that unlike ionic compounds, which are all found as crystalline solids at room temperature, covalent compounds, you'll find them as gases, liquids, and solids at room temperature. And again, that has to do with the intermolecular forces. Some compounds will have stronger intermolecular forces than others. Some will have weaker. To illustrate this, this is a diagram of solids, liquids, gases. So each of those blue circles represents a covalently bonded compound or molecule. In order for something to be a solid at room temperature, like we see in the diagram on the far left, that must be that it has high or strong intermolecular forces. An example of this would be sugar. So although sugar will melt pretty easily, if you've ever put sugar in a frying pan, it melts pretty quickly. But it is a solid at room temperature. Molecules that are liquids at room temperature have weaker intermolecular forces. So these guys stick together enough that they're going to stay in the liquid phase, but they're able to roll past one another and break and reform intermolecular forces. An example of this would be water. Water is a liquid at room temperature. And then a lot of covalent compounds are found as gases, and we're going to consider that these guys really at room temperature have no intermolecular forces. They're so weak that they barely stick to each other. And so because they barely stick to each other, they just fly away from one another and go all over the place. Again, I want to stress the difference between an intermolecular force and a covalent bond. Here is a sample of water. It's pretty orderly, so I would probably say that this is a solid. So maybe this is solid ice. The covalent bond are these lines. Those are the covalent bonds. These come from hydrogen and oxygen sharing electrons. It is a very strong bond. The thing holding one water molecule to another are intermolecular forces. And for water, we're going to learn this is a special intermolecular force called hydrogen bonding. And hydrogen bonding is a lot weaker than covalent bonds. It doesn't take that much to melt ice. So if this is a sample of ice, a bunch of water molecules arranged in an organized pattern, to melt ice, what I need to do is take one of these water molecules and kind of pull it apart and break that hydrogen bond. And that doesn't take that much to do. I can do that. I can pull these apart and make water actually kind of melt into a liquid where those hydrogen bonds have now been weakened. They're still there because they still stick to each other enough to form, to keep it as a liquid so they stay together. But notice that water, it can flow, right? These molecules can flow past one another. They can move around because of the fact that it has weak intermolecular forces. Another example of a covalently bonded compound is methane, CH4. Again, the covalent bond is the line. This is a very, very strong bond. Methane does not have strong intermolecular forces. These methane molecules have no attraction to one another. And so methane zips all over the place and is a gas at room temperature. Okay? So you'll find that covalently bonded molecules in all three states of matter at room temperature. The third property we want to talk about is the fact that covalent compounds in general will not conduct an electric current when dissolved in water. So let's kind of spend a little time talking about what that means. An electrolyte is something whose aqueous solution, now this is a word that is important. Aqueous means dissolved in water. So an aqueous solution is when you take something and you dissolve it in water. So for example, I take some salt, I dissolve it in water, that forms an aqueous sodium chloride solution. I take some sugar, I dissolve it in water, that forms an aqueous sugar solution. When you have something that when you dissolve it in water, it forms ions that can move, it will be able to conduct an electric current. Because in order to conduct an electric current and to be an electrolyte, what you need is to have mobile ions. So the key to being an electrolyte is the presence of mobile ions, ions that can move. Non-electrolytes are substances that will not form ions in solution and will not conduct an electric current. We're going to see that ionic compounds will form ions in solution and covalent compounds will not. To illustrate this, let's look at this beaker of water. So here is a beaker of water with H2O molecules. And what we're going to look at is what happens if I put the ionic compound NaCl in. When you put NaCl in water, what is going to happen is that its ions are going to dissociate. They are going to break apart. Once in water, these ions are free to move and flow around. And since you've got mobile ions, they can conduct an electric current. If I were to put electrodes in here, they would be able to move these ions and carry an electric current. That is ionic compounds. In contrast, If you put a covalent compound in, like ammonia NH3, covalent bonds are strong. Remember, nitrogen is covalently bonded to hydrogen in NH3. And those bonds are not going to break just because you put them in water. So when I put ammonia in water, it doesn't fall apart. It does not dissociate. The covalent bonds do not break, and it does therefore not form ions and does not conduct an electric current. Another example of a covalent compound that does not form ions in solution is glucose. Glucose is C6H12O6. If you put that in water, again, these blue lines represent covalent bonds. The carbon is covalently bonded to the oxygen. The oxygen is covalently bonded to the hydrogen. You will not break those covalent bonds when you put them in water. You will not form ions, and you are therefore not going to be able to conduct an electric current. Another example would be ethanol. Ethanol is another covalent molecule, C2H5OH. This is basically alcohol, right? What we drink for alcohol. It will not form ions when you put it in solution and is, again, also a non-electrolyte.